Welcome back, everybody. Today is L function day. So this is going to seem a little bit disjoint from the previous topics, but we're still in chapter 3 of my notes, and we will tie this into modularity. So first, let's look at the Tate module of an abelian variety. We're going to discuss L functions briefly this video. We're going to do so in a broader sense than strictly necessary because we want to talk about general abelian varieties and not just elliptic curves. If you want to see simpler constructions for L functions that apply only to elliptic curves, I would just read the Silverman books, especially like Silverman 1, chapter 7 in the appendix. So let's let A be an abelian variety over Q with dimension G. Remember, an abelian Q variety is just a kind of like a complete group variety, like an elliptic curve. An elliptic curve would be a dimension 1 abelian variety. So akin to the theory of elliptic curves, for each prime L, there's an L-adic representation, rho sub L, from the absolute Galois group of Q to aught of V sub L of A, which is isomorphic to GL sub 2G of Q sub L, the L-adic numbers. Okay, so if G is 1, this is just your usual L-adic representation attached to the elliptic curve to GL2 of QL. Okay, and here VL of A is the Tate module of a T sub L of A tensor with Q sub L over C sub L. Okay, so this is like the rational Tate module. And so what's the Tate module? Well, it's the same thing as it was for elliptic curves. T sub L of A is just the inverse limit over n of the L to the n torsion of A. Okay, so all of this is more or less the same as the theory of Tate modules of elliptic curves, but we just have this extra kind of G floating around here. Just some definitions from basic representation theory. Let's let rho star sub L be the contragradient representation on the dual space of V sub L of A, which we'll denote by V star sub L of A. In general, what is a contragradient representation or a dual representation? If I give you a representation rho from some group to aught V, where V is some vector space, rho star from G to aught V star, given by rho star of G, is rho of G inverse transpose. That's the contragradient representation kind of attached to or associated to rho. Okay, so it's like just a natural representation on the dual space of a given vector space, given a representation on that vector space. Okay, let's define local L factors now. If P is a prime, we'll define what we'll call the local L factor at P sub P of AT. T is a variable here, by determinant of 1 minus T times rho star sub L of sigma sub frac P inverse on V star sub L of A. And then I have this kind of superscript I of frac P, and I'll explain all this. Okay, here L is any prime that isn't P, which is remarkable. Okay, I of frac P denotes the inertia group at frac P. We defined that several videos ago. Okay, so that's where the residual action is trivial. Sigma sub frac P denotes a Frobenius element at some prime frac P of Q bar lying over P. It doesn't actually matter which prime frac P you pick. And what is this? What is the superscript I of frac P? That's all I have to explain. Well, it's basically the stuff in V star sub L of A that's fixed by the inertia, the action of inertia. So it's all the stuff, it's all the V in V star sub L of A, such that rho star sub L of G acting on V just equals V for all G in inertia at frac P. Okay, so like when you see an object in this context with a superscript attached to it, that usually just means you're looking at all of the things kind of in the base here that are fixed by the stuff in the superscript. Okay, now this is a polynomial because it's a determinant. Okay, it's easily seen to be independent of choice of frac P and sigma sub frac P. Remember, sigma sub frac P is an actual equivalence class of objects. So technically you could change frac P and sigma sub frac P, but this polynomial is independent of both choices, basically because prime ideals of Q bar lying over P are Galois conjugate. That's something you learn in a basic algebraic number theory book or course. Now, there are some deeper facts about this local L factor. It's actually a polynomial over Z and T. That's not obvious. And also not obvious, remember here I said L could be any prime not equal to P. Well, that's because it turns out that P sub P of AT is independent of the choice of L. Now, that's also not obvious. And this follows from Grothendieck's semi-stable reduction theorem, which says essentially that every abelian variety over a global field K, like a number field, has semi-stable reduction over some finite extension of K. So you can always move up to a finite extension of the ground field and acquire semi-stable reduction. The original references for this would be like Grothendieck's monodromy stuff in SGA 7. Maybe more modern references, though, would be, I don't know how to say this, Liedtke, semi-stable reduction for curves, followed by Conrad's semi-stable reduction of abelian varieties. I think these are great references. Okay, you can also see like Silverman 1 chapter 9 for the much simpler elliptic curve case. Okay, how about roots of the local L factors? I mean, they're polynomials, right? So we can factor them. Okay, so I mean, they're polynomials of degree 2g. So let's factor p sub p of at into a product of root normalized roots, 1 minus alpha sub I pt. Okay, and these alpha sub I p's, they're just complex numbers. It's a theorem that the, oh, this should be alpha, sorry. It's a theorem that the absolute value of alpha sub I p is less than or equal to root p for all I, with equality if p is a prime of good reduction for the abelian variety A. For elliptic curves, this theorem is just the Hasse bound combined with the Weil conjectures for elliptic curves, and this is all covered in Silverman 1, chapter 7. So we can actually get a handle on the size of these roots. Okay. These root coefficients, I guess you could say. Now, so what is the global L function? Basically, this discussion up here gives me that there's an Euler product, which I'll call L of AS, which is the product over P of the reciprocals of the local L factors where T has been replaced by P to the negative S, a substitution motivated by the Riemann zeta function. This is the global L function attached to A. Okay, so it's like the product of the reciprocals of all the local L factors, basically. And this product converges for a real part of S bigger than 3/2. And it's another consequence of semi-stable reduction, which we just talked about, that you can attach to A a conductor and n of A, just like you can for elliptic curves, and a sign, plus or minus, which we call the root number, W of A. So it's either plus or minus 1. For this stuff, you can see I gave you some Serre references, some Deligne references. And both of these references, I believe, are actually in modular functions of one variable too. And I said in a previous video, you should probably just get all the modular functions of one variable books. There's 4 or 5 of them that come up in my lecture series here. I don't remember exactly how many. Okay, so details can be found there. So what is this conjecture that's in the title of the video? Well, so I'll call it conjecture 1. Here's what it says. It says, let's let lambda of AS be the conductor of A to the S over 2 power times 2 pi to the negative S gamma of S, where gamma of S is just the usual gamma function, all to the G power. Remember, G is the dimension of A here, times the L function of A. The conjecture is that lambda of AS has an analytic continuation to an entire function. Remember, right now, its Euler factor only converges for a real part of S bigger than 3/2. But we conjecture that when we kind of staple on some stuff on the front here, we get a full analytic continuation to the entire complex plane, okay, of order 1 with functional equation. So I can, not only is there an analytic continuation to all of C, but there's actually a functional equation relating the values of lambda at S and 2 minus S for each S. And that functional equation purportedly is lambda of AS equals WA, where WA is the root number. It's either plus or minus, depending on the abelian variety, times lambda of A 2 minus S. Okay, and so we'll see how this ties into modularity next time. You might, again, even be left scratching your head right now, like why I'm talking about this stuff, but you'll see soon. And so stay tuned for the next video, and thanks for watching.